Hi Mark, I'm Doris. My student number is S04411031. I'm the freshman of the NCUE. The video title is The New Bionics That Let Us Run, Climb, and Dance. Looking deeply inside nature, through the magnifying glass of science, designer exact principles, process, and material they are forming the very basis of design methodology, from synthetic constructs that resemble biological materials to computational methods that emulate natural processes. Nature is driving design. Design is also driving nature. In realms of genetics, regenerative medicine, and synthetic biology, designers are growing novel technologies not foreseen or anticipated by nature. Bionics explore the interplay between biology and design. As you can see, my legs are bionic. Today, I will tell human story of bionic integration, how electromechanics attached to the body and implant inside the body are beginning to bridge the gap between disability and ability, between human limitation and human potential. Bionics has defined my physicality. In 1982, both of my legs were amputated due to tissue damage from frostbite incurred during a mountain climbing accident. At that time, I didn't view my body as broken. I reasoned that a human being can never be broken. Technology is broken. Technology is inadequate. This simple but powerful idea was a call to arms to advance technology for the elimination of my own disability and ultimately the disability of others. I began by developing specialized limbs that allow me to return to the vertical world of rock and ice climbing. I quickly realized that the artificial part of my body is malleable, able to take on any form, any function, a blank slate for which to create perhaps structure that could extend beyond biological capability. I made my head adjustable. I could be as short as 5 feet or as tall as I like. So when I was feeling bad about myself, insecure, I would jack my head up. But when I was feeling confident and suave, I would knock my head down a notch, just to give the competition a chance. Narrow edge feet allow me to climb steep rock fissures where the human foot can not penetrate, and big feet enable me to climb vertical ice walls without ever experiencing muscle leg fatigue. Through technological innovation, I returned to my sport, stronger and better. Technology had eliminated my disability and allowed me a new climbing prowess. As a young man, I imagined a future world where technology so advanced could rid the world of disability, a world in which neutral implants will allow the visually impaired to see, a world in which the paralyzed could walk via body exoskeleton. Sadly, because of deficiencies in technology, disability is rampant in the world. This gentleman is missing 3 limbs. As a testimony to current technology, he's out of the wheelchair, but we need to do a better job in bionics to allow, one day, for rehabilitation for a person with this level of injury. At the MIT Media Lab, we'll establish the Center of Extreme Bionics. The mission of the center is to put forth fundamental science and technological capability that will allow the biomechatronic and regenerative repair of humans across a broad range of brain and body disabilities. Today I'm going to tell you how my legs function, how they work as a cast-in point for this center. Now I made sure to shave my legs last night because I knew I'd be showing them off. Bionics entails the engineering of extreme interface. There's 3 extreme interfaces in my bionic limbs. Mechanical, how my limbs are attached to my biological body. Dynamic, how they move like flesh and bone. And electrical, how they communicate with my nervous system. I'll begin with mechanical interface. In the area of design, we still do not understand how to attach device to the body mechanically. It's extraordinary to me that in this day and age, one of the most mature, oldest technology in the human timeline, the shoe, still gives us blister. How can this be? We have no idea how to attach things to our bodies. This is the beautifully lyrical design work of Professor Neri Osman at the MIT Middle Lab, showing spatially varying exoskeletal impedances shown here by color variation in the 3D printed model. Imagine a future where clothing is stiff and soft where you need it, when you need it for optimal support and flexibility without ever causing discomfort. My bionic limbs are attached to my biological body via synthetic skin with stiffness variations that mirror my underlying tissue biomechanics. To achieve that mirroring, we first develop a mathematical model of my biological limb. To that end, we use measuring tools such as MRI to look inside my body to figure out the geometries and location of various tissues. We also took robotic tools, use a floating acupuncture circle that goes around the biological limb. The acupuncturists come in, find the surface of the limb, measure its unloaded shape, and then they push on the tissue to measure tissue compliances at each anatomical point. We combine this imaging and robotic data to build a mathematical description of my biological limb. Shown on the left, you see a bunch of points or knots. At each knot, there's a color that represents tissue compliance. We then do a mathematical transformation to the design of the synthetic skin, shown on the right, and we'll discover optimality is where the body is stiff, the synthetic skin should be soft. Where the body is soft, the synthetic skin is stiff, and this mirroring occurs across all tissue compliance. With this framework, we produce bionic limbs that are the most comfortable limbs I've ever worn. Clearly, in the future, our clothing, our shoes, our breasts, our prosthetics will no longer be designed and manufactured using artisan strategy, but rather data-driven quantitative frameworks. In that future, our shoe will no longer give us blister. We're also embedding sensing and smart material into the synthetic skin. This is a material developed by SRI International, California under electrostatic effect. It changes stiffness. So under zero voltage, the material is compliant. It's floppy like paper. Then the buttons push, a voltage is applied, and it becomes stiff as a ball. We add this material into the synthetic skin that attach my bionic limb to my biological body. When I walk, here is no voltage. My interface is soft and compliant. The buttons push, voltage is applied, and it stiffens, offering me a greater maneuverability over the bionic limb. We're also building exoskeletons. This exoskeleton becomes stiff and soft in just the right areas of the running cycle to protect the biological joints from high impacts and degradation. In the future, we'll all be wearing exoskeletons in common activities such as running. Next, dynamic interface. How do my bionic limbs move like flesh and bone? At my MIT lab, we study how humans with normal physiological stand, walk, and run. What are the muscles doing, and how are they controlled by the spinal cord? This basic science motivates what we build. We're building by neck, ankles, knees, and hips. We're building body parts from the ground up. The bionic limbs that I'm wearing are called bumps. They've been fit to nearly 1,000 patients, 400 of which have been wounded U.S. soldiers. How does it work? At heel strike, under computer control, the system controls stiffness to attenuate the shock of the limb hitting the ground. Then at mid-stance, the bionic limb outputs high torques and powers to lift the person into a walking stride, comparable to how muscles work in the calf region. This bionic propulsion is very important clinically to patients. So on the left, you see a bionic device worn by a lady. On the right, a passive device worn by the same lady that fails to emulate normal muscle function, enabling her to do something everyone should be able to do: go up and down their step at home. Bionics also allows for extraordinary athletic feats. Here's a gentleman running up a rocky pathway. This is Steve Martin, not a comedian who lost his leg in a bomb blast in Afghanistan. We're also building a skeletal structure using the same principle that wrap around the biological limb. This gentleman does not have any leg condition, any disability. He has a normal physiology, so this exoskeleton are applying muscle like torques and powers so that his own muscles need not apply those torques and powers. This is the first exoskeleton in history that actually augments human working. It significantly reduces metabolic cost. It's so profound in its augmentation that when a normal healthy person wears the device for 40 minutes and then take it off, their own biologic leg feel ridiculously heavy and awkward. We're beginning the age in which machines attached to our body will make us stronger and faster and more efficient. Moving on to electrical interface, how do my bionic limbs communicate with my nervous system? Across my residual limb are electrodes that measure the electrical pulse of my muscles that's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desires. This diagram shows fundamentally how the bionic limb is controlled. So we model the missing biological limb and we'll discover that reflexes occur, how the reflexes of the spinal cord are controlling the muscles, and the capability is embedded in the chips of the bionic limb. What we've done this is we modulate the sensitivity of the reflex, the model spinal reflex with the neural signal, so when I relax my muscles in my residual limb, I get very little torque and power, but the more I fight my muscles, the more torque I get, and I can even run. And it was the first demonstration of a running get under neural command. Feels great. We want to go a step further. We want to actually close the loop between the human and the bionic external limb. We're doing experiments where we're growing nerves, transecting nerves through channels or microchannel areas. On the outer side of the channel, the nerve then attaches to cells, skin cells, and muscle cells. In the motor channels, we can sense how the person wishes to move. They can be sent out wirelessly to the bionic limb. Then, on the bionic limb can be converted to stimulations in adjacent channel, sensory channel. So when this is fully developed and for human use, persons like myself will not only have synthetic limbs that move like flesh and bone, but actually feel like flesh and bone. This video shows Lisa Maletta shortly after being fit with 2 bionic limbs. Indeed, bionics is making a profound difference in people's lives. Oh my god, I can't believe it. It's just like I've got a real leg. Now, don't start running. Now turn around and do the same thing walking up, but get on your heel to talk. Like you would normally just walk on level ground, try to walk right up the hill. Oh my god, is it pushing you up? Yes, I can't even describe it. It's pushing you right up. Next week I'm visiting the center. Thank you. Next week, I'm visiting the Center for Medicare and Medicaid Service, and I'm going to try to convince CMS to grant appropriate code language and pricing so this technology can be made available to the patients that need it. Thank you. It's not well appreciated, but over half of the world's population suffers from some form of cognitive, emotional, sensory, or motor condition, and because of poor technology, too often conditions result in disability and a poor quality of life. Basic level of physiological function should be a part of our human rights. Every person should have the right to live life without disability if they so choose. The right to live life without severe depression, the right to see a loved one in the case of seeing impaired, or the right to walk or to dance in the case of limb paralysis or limb amputation. As a society, we can achieve these human rights if we accept the proposition that humans are not disabled. A person can never be broken. Our built environment, our technology are broken and disabled. We the people need not accept our limitation but can transcend disability through technological innovation. Indeed, through fundamental advances in bionics in this century, we will set the technological foundation for enhanced human experience and we will end disability. I'd like to finish up with one more story, a beautiful story, the story of Adrienne Haslett Davis. Adrienne lost her leg in the Boston terrorist attack. I met Adrienne when this photo was taken at Sporting Rehabilitation Hospital. Adrienne is a dancer, a ballroom dancer. Adrienne breathes and lives dance. It is her expression. It is her art form. Naturally, when she lost her limb in the Boston terrorist attack, she wanted to return to the dance floor. After meeting her and driving home in my car, I thought, I'm an MRT professor. I have resources. Let's build her a bionic limb to enable her to go back to her life of dance. I brought in MIT scientists with expertise in prosthetics, robotics, machine learning, and biomechanics, and over a 200-day research period, we studied dance. We brought in dancers with biological limbs, and we studied how they move, what force they apply on the dance floor, and we took those data. And we put forth fundamental principle of dance, reflexive dance capability, and we embed that intelligence into the bionic limb. Bionics is not only about making people stronger and faster. Our expression, our humanity can be embedded into electromechanics. It was 3.5 seconds between the bomb blast in the Boston terrorist attack. In 3.5 seconds, the criminals and cowards took Adrienne off the dance floor. In 200 days, we put her back. We will not be intimidated, brought down, diminished, conquered, or stopped by acts of violence. Ladies and gentlemen, please allow me to introduce Adrienne Haslett Davis, her first performance since the attack. She's dancing with Christine Linter. Ladies and gentlemen, members of the research team, Elliot Rose and Nathan Villagarakowski. Elliot and Nathan,